My name is Garrett Duling, and I will be presenting on the undamageable material. And I worked on this content with Molly Brombaugh, Evan Berger, Grant Crownhart, and Ian Ferdowsian. In the paper we read, the damage variable was defined as a script L. However, we used lambda here just so it's a little clearer with the notation. And the damage variable quantifies the material degradation from an undamaged state. So you start with your initial modulus, E naught, minus your final modulus, which will be your damaged state, over E, which is your final modulus. And this ranges from 0, where there's no damage, to 1, where it's complete damage. And this reflects the total reduction in the load-bearing capacity. Related to the undamageable material, we have the energy equivalence hypothesis. This is the damaged material's response is equivalent to an undamaged material with reduced stiffness. And we see this with our elastic energy, as notated below, and with the resulting stress relation as you derive it out based on the undamageable coefficient, or the damage variable, lambda. And this implies that stress increases with damage, but we will see that stress can also be independent of damage with higher order energy relationships. This slide covers the derivation of some higher order energy equivalences. And so here we see our relation with elastic energy and our stress strain relation based on a unknown coefficient n, or a variable n. And as we take n to go to infinity, we see that our initial stress is equal to our final stress. And this implies that stress is independent of the damage variable lambda because it does not appear in our stress strain relation in the limiting case. The material exhibits no degradation regardless of damage accumulation, and this is similar to setting the stretch ratio equal to 1. To show our stress strain relationships in the form of energy, we first start with the integral of stress d strain, where stress is equal to the energy times some function of strain. And so when we derive with respect to strain, we end up with that function there, which is 1/2 times the function prime of strain times strain squared plus the function of strain times strain minus the function of strain has to be equal to 0. And so when we solve for our stress, we get that stress is related to the modified elastic modulus and the material constant depending on n, that power that we had before. In order to visualize the effect of the order of our energy equation, we can use this plot to see that as our n increases, we are slowly approaching a horizontal line. And so as it approaches that horizontal line, stress remains constant regardless of strain, such that there's no accumulation of stress. This means that as n increases, the material becomes more resistant to damage, and there is a theoretical limit as n approaches infinity where the material is undamageable as it does not accumulate stress. So the challenges in realizing an undamageable material lie in the energy equivalence control and the fact that we cannot make these materials. So the precision to which you have to control the material properties is very significant as you're changing that n value. As we saw before, it lies in several terms in our equations for our derivation of stress with relation to our order of n. And there's also the mathematical complexities of extending theory to 3D, which introduces the nonlinear equations, which means that we also can't manipulate them as well. And it also requires very complex numerical methods, which are computationally expensive. And there's also the limitations of material imperfections. So as you make a material, you're going to inherently introduce imperfections, and these will limit your ability to not accumulate stress in a material with strain. To do an example for this topic, we're going to look at the way you get from the energy to the corresponding stress-strain relation for the higher order terms, or as you increase your value of n. And so to do this, we are going to go through this table and show the derivation from left to right. We will start with the general form of the higher order strain energy, where we have K is equal to N. And so to approximate the area under the stress strain curve, we're going to do 1/2 of a function of strain to the N. And in order to move to our energy to our stress, we're going to have Hooke's law, where stress is equal to the modulus times strain. This is where we end up with 1/2 the modulus times the function of strain times strain to the N. When we take the derivative of that function with respect to strain, we end up with du is equal to, this is going to be the partial of u with respect to strain, is equal to 1/2 modulus times the function primed of strain times strain to the n, plus n over 2 times modulus function of strain to the n minus 1. And then as we simplify out where du is equal to e, or the modulus times the function of strain d strain, we move into a different form below where the differential equation is solved, where the function of strain is equal to e to the some constant times 1 over strain to the n times the exponential of -2 over n minus 1 times the exponent of n minus 1. And if we substitute this back into Hooke's law above, where we said that stress is equal to the modulus times strain, we end up with stress is equal to the modulus times 1 over strain to the n times the exponent of -2 over n minus 1 times e to the n minus 1. And this is the same form as the last row in that table in 16.1.